After the government wrote off North American Aviation Airframe serial number 44-83887, the surviving structure passed into Walter Saplata's hands and spent decades in the open on his Ohio farm. The prototype had already been reduced to a damaged shell, so Plata acquired the remains without the original engines or propellers and moved them to his Newberry property. For many years, the aluminum alloy stressed skin and primary structural components lay exposed to the elements. The environment imposed relentless weather cycling. Seasonal temperature variations expanded and contracted the metal while standing water pooled in open structural sections. This open-air corrosion process broke down protective coatings and induced widespread oxidation across the airframe. The integrity of the original alloy degraded with each passing winter. The scrap heap contained only the port fuselage, sections of the shattered center wing, and scattered components belonging to the right side of the aircraft. Unprotected from rain and snow, the exposed rivets and structural ribs experienced deep galvanic corrosion where dissimilar metals touched. Moisture trapped beneath the wreckage kept the lower surfaces wet, making the lower fuselage frames especially vulnerable. By the time the recovery team assessed the prototype, the lower skin could not support the upper fuselage, so every surviving piece had to be documented before anything moved. They cataloged the port fuselage section and mapped the decay patterns to determine which underlying bulkheads remained structurally viable. Despite the severe material degradation, the scattered components retained a unique forensic signature. When Tom Riley purchased the remains from the estate in 2008, the initial survey required positive identification of the specific prototype. Investigators located a preserved factory fabrication mistake on the left fuselage skin. During original manufacturing, the static airport was initially positioned incorrectly, then repositioned before the aircraft was completed. Rather than erasing the evidence entirely, the factory left a pattern of plugged holes beside the correct static airport location. This exact pattern of plugged and active holes matched the documented configuration of the specific experimental airframe. It became a key authenticity marker, tying the restored skin back to the original prototype instead of to a generic production model. The discovery confirmed that the scrap pile held the authentic second prototype, distinguishing it from standard production models. This verified identity turned the rebuild into a prototype-specific forensic project. Every new part had to match airframe 4-83887. The transition from scrapyard to restoration facility secured the artifact, but exposed massive gaps in the physical inventory. The remaining pieces represented a fraction of the total required structural mass. Transport required custom cradles that spread the load across the surviving sections before the wreckage could leave the farm. That stabilization phase also set the proof limit for the factory mistake. The whole pattern was recoverable, even though the wreckage itself had been cut, stored, and damaged for decades. The team needed to understand exactly how the aircraft had been dismantled to determine what was permanently lost. What mechanical events reduced a high-altitude prototype to scattered aluminum sections in the mud? The loss of directional control on an icy paved runway and the subsequent use of a chainsaw dictated the survival geometry of the aircraft. On December 14, 1949, according to NASA's later history of the accident, the prototype was operating from the NACA Flight Propulsion Laboratory at Cleveland Municipal Airport. The National Advisory Committee for Aeronautics had acquired Airframe 4-83887 in October 1947 for the early phase of an air-launched ramjet research program. This mission profile required specific modifications. Engineers fitted the right wing area to carry the experimental ramjet missile installation. These changes left a distinct ramjet overprint on the airframe. The installation mattered less as a generic weapons fit than as a research configuration, with racks, fittings, and instrumentation tied to the NACA test program. This operational context explains the exact configuration of the aircraft on the day of its loss. The initiating failure occurred during a winter operation after a research flight. The prototype hit patches of ice, skidded sideways off the runway, and dropped into soft mud beyond the pavement. The wheels sank deeply after unseasonably warm weather had softened the ground. The propellers, radiator housing, center section, and gear structure were damaged badly enough to make repair uneconomical, even though the crew survived and the aircraft was not consumed by fire. The result was not a fire loss, but a badly distorted airframe. Because the damage made repair uneconomical for an obsolete experimental testbed, the government struck the aircraft from active inventory. The decision to scrap the airframe triggered the most destructive phase of its history. To remove the bulk mass from the mudbank and later move it to private storage, the airframe had to be reduced to transportable sections. The prototype featured a massive, continuous center wing section that joined the two fuselages. This component contained the heavy machine gun bay and the primary load path for the entire aircraft. For transport, sources describe the center section being cut apart with a torch rather than a chainsaw, permanently breaking the aircraft's unified geometry. The break was more than cosmetic. The continuous load path had been destroyed, and any heat affected, distorted, or missing material had to be treated as lost structure rather than reusable strength. Rebuilding the primary structure required mapping what survived, discarding compromised edges, and reconstructing the geometry from factory drawings and purpose-built fixtures. The combination of the runway excursion damage, the ramjet modification trace, and the intentional scrapyard severance created a massive engineering deficit. Reversing these three destructive layers demanded an extreme application of labor. The restoration team ultimately committed 207,000 labor hours to correct the physical deficit and return the metal to its original blueprint specifications. The magnitude of this labor quantified the true cost of the scrap crew decision. With the damage quantified, what prevented the restoration team from simply buying surplus fighter parts to bridge the gap? The visual similarity between the standard single-engine variant and the dual-fuselage prototype masked a complete structural contradiction. To solve the structural gap, the logical step would involve sourcing abundant surplus parts from the standard Mustang inventory. However, the external shape of the prototype was deeply deceptive. The aircraft shares less than a handful of interchangeable parts with the single-engine model. Items like the elevator trim wheel and canopy crank crossed over, but primary structural components required entirely separate engineering. The original manufacturer invested 204,000 engineering hours in the standard single-engine design. By contrast, developing the dual-fuselage prototype demanded 1,470,000 original engineering hours. This massive dimensional divergence meant that the major landing gear structure, wing structure, fuselage bulkheads, and system routing could not be treated as ordinary single-engine Mustang stock. The structural mismatch turned the rebuild into a hard supply chain failure. Replacement parts could not be ordered. They had to be fabricated or scavenged from the same rare type. Only 5 total surviving airframes of any variant existed globally. Finding matching components required continental surveys. Sourcing these rare parts became an archaeological exercise. The team mapped known crash sites, forgotten military storage yards, and private collections. Every recovered piece had to be inspected for hidden corrosion, metallurgical fatigue, and dimensional accuracy before it could be integrated into the rebuild. That divergence reached the aircraft's skin. The Twin Mustang used lengthened fuselage sections behind the cockpits and a center wing built around 2 engines, heavy fuel loads, and a shared weapons bay. Missing aluminum had to be formed from Twin Mustang drawings, surviving parts, and custom tools. The most critical engineering requirement centered on the propulsion system. The aircraft utilized 2 powerful Merlin engines mounted on separate fuselages. The aircraft used counter-rotating propellers to cancel the torque and gyroscopic penalties of 2 Merlins. On the restored prototype, the revised inward turning arrangement kept the aircraft far more stable during takeoff and high-power operation. One propeller's rolling torque opposed the other instead of doubling it. This aerodynamic requirement dictated rare engine and propeller hardware. The restoration needed the correct Packard Merlin pair, a V-1650-23 and a V-1650-25, with the left and right sides built to support the counter-rotating propeller system. The reverse rotation hardware was not a matter of ordinary surplus substitution. Because the prototype was heavily damaged and stripped during its scrapyard years, these critical engine and propeller components were missing. The search forced investigators to look far beyond standard aviation supply lines. How can a restoration proceed when the required left-turning hardware is extinct? Investigators tracked rumors and serial numbers across international borders for the missing left-hand turning power plant. The search finally turned when Mike Nixon of vintage V-12 located a brand new Packard Merlin V-1650-23 in Mexico City, still in its box. The find gave the team a viable foundation for inspection, overhaul, and certification work, not a flight-ready engine by assumption. Procuring the engine solved only half of the thrust problem. The counter-rotating installation also required propellers that could safely reproduce the left and right geometry of the original Aero product system. Airworthy originals were not available at any price. The restoration team therefore accepted a limited material deviation. MT Propeller in Germany manufactured modern composite replica propellers for the project. This preserved the essential counter-rotating geometry while removing the unacceptable risk of flying corroded or unavailable original blades. The propeller solution still required rigorous mechanical discipline. The new assemblies had to match the required rotation, pitch behavior, blade clearance, and vibration limits before they could be trusted on the airframe. A propeller failure on a twin fuselage prototype would not be a minor defect. It could create violent asymmetric drag and yaw. For that reason, the team treated the propeller installation as a flight safety system, not as a display detail. The blade still had to transmit the torque of the 12-cylinder engines without departing from the intended aerodynamic envelope. With the thrust geometry solved, how far would the team go to preserve the original prototype exact identity? The decision to source replacement components from extreme environments required a massive logistical network. To replace the shattered internal bulkheads and missing skin panels, the restoration team had to hunt for salvage parts scattered across the continent. They recovered and purchased Twin Mustang structural material and reference parts from several scattered sources, including Alaska, Colorado, South Florida, and private collections. Some pieces were usable hardware, others were patterns, clues, or dimensional references for newly fabricated parts. Consolidating these isolated artifacts into a single cohesive structure demanded strict forensic discipline. Every piece had to be cataloged, stripped, inspected for microfractures, and matched against the master blueprints. The parts sourced from different regions presented different inspection problems. Alaska and Colorado material had to be checked for cracks, distortion, missing structure, and previous crash damage. South Florida parts demanded careful corrosion inspection because humidity can hide damage inside seams and overlaps. Only verified parts could enter the rebuild. The verification process dictated the timeline. Cleaning, checking, and fitting the salvaged parts consumed 10.5 years. The team could not accelerate the build without compromising the structural integrity of the airframe. The integration of Alaskan, Colorado, and Florida components required custom alignment jigs. Because each salvage part had experienced different environmental stresses during its lifetime, the mating surfaces rarely aligned perfectly on the first attempt. Mechanics had to carefully adjust the rivet lines, ensuring that the load path remained continuous across components that had never originally been assembled together. Despite the diverse origin of the internal parts, the outer skin had to reflect the second prototype's documented identity. During reconstruction of the port fuselage, engineers replaced the corroded scrapyard metal with new aluminum panels, then recreated the documented plugged hole sequence for the incorrectly positioned pitot-static vent. The replicated flaw was not absolute proof by itself. It was one controlled marker inside a broader discipline in which rivets, flush patches, and filled holes followed the surviving record as closely as the evidence allowed. The effort transformed a chaotic collection of salvaged parts and newly fabricated aluminum into a rigid flight-capable structure. The static restoration was complete, but the mechanical systems had to be tested under live power. Would the forensic perfection of the static airframe survive the physical stresses of live engines? Applying 55 inches of manifold pressure to a lightly loaded airframe triggered a critical risk constraint on the runway. On the final day of the year, the restoration team conducted a mandated high-speed taxi test. The objective was purely procedural. The pilot needed to evaluate the ground handling characteristics, verify the steering geometry, and confirm that the counter-rotating thrust canceled the torque as designed. The aircraft was configured in a stripped-down state. It carried minimal fuel and lacked the heavy military equipment that typically burdened the type. The restored prototype weighed approximately 14,700 pounds during the test context, light enough to make the power-to-weight ratio immediately apparent. The pilot advanced the throttles to evaluate acceleration. The engine spooled up to a combined 3,720 horsepower, and the planned ground check instantly became a power-to-weight problem. Acceleration built far faster than expected. The aircraft accelerated down the paved surface far faster than the team expected. The new left and right composite replica propellers bit into the dense winter air, converting 3,720 horsepower into massive forward kinetic energy. Within seconds, the airflow over the custom fabricated wing ribs generated significant lift. The heavy tail lifted off the ground. The pilot realized the acceleration curve was unrecoverable within the confines of a ground test. The airframe wanted to fly. The pilot faced a hard mathematical boundary. The remaining runway could not safely absorb the aircraft's speed. Applying maximum wheel braking at that velocity would likely lock the tires, blow the rubber, and send the meticulously restored prototype skidding off the pavement, exactly mimicking the 1949 loss mechanism. The bounded mechanism of the braking limit dictated the outcome. The pilot judged that the remaining runway would make getting back down and stopping marginal. To control the risk, the test pilot made a rapid operational decision. The pilot chose the safer option and pushed the power back up. On December 31, 2018, the aircraft unexpectedly broke ground and entered an unplanned first post-restoration flight. He kept the aircraft moving, trading speed for altitude to buy time and secure a safe traffic pattern. The pilot maintained the flight for 5 minutes. During this brief window, the pilot evaluated the flight controls and watched the engine temperatures and pressures. The landing gear remained down throughout the short flight, turning the event into a controlled gear-down circuit rather than a full systems test. The counter-rotating thrust geometry held the dual fuselages stable. After 5 minutes, the pilot made a controlled approach and used the full runway to bleed off the remaining speed. The official first post-restoration flight followed on January 28, 2019, confirming that the aircraft had survived the mud, the torch, and the extreme supply chain failure to return to the air as close as practical to the operational geometry of its original 1940s design.